Hey everyone, welcome back to another video from Smart Interviews. So today we are going to discuss the problems under CodeChef Starters 187. I'm 𝗟𝗲𝗃𝗲𝗹. Let's get started.
If you look at the first problem, exercise and rest. Chef is on a new exercise plan. He will work out for 2 days, then take 1 day rest, and then repeat. Today is Chef's nth day rest. How many days, including today, has it been since Chef started his plan? Okay, so you're supposed to find like in since how many days he has started his plan. You're given only integer input. For this given input, you're supposed to say it has been how many days that he has started his particular plan. So if you look at this particular example, if we assume like he's a chef, so let us say this is a day 1 and this is day 2, and on the third day what he does, he does not do any exercise, he just simply take a rest, and this is third day. In other terms, this is the first day of chef's rest, and this is day 4, day 5, and this is day 2 of chef's rest. In other terms, as this is day 2, since 6 days he's continuously working. Like since his 6 days he just started his workout. So this can be answer for this. I guess this is not really a very tough problem. We can just simply solve this by saying like 3 times or number of days is going to be output for this example. So let us just quickly code it up. Let us first take scanner class. Scanner sc equals to scanner of system dot in int 3 times of it seems 6. Let us just quickly compare with the sample input output. Yeah, for 2 output should be 6. Let us submit this. All the test cases work first. Moving to the next one, Choco Cut. Alice has a rectangular bar of chocolate of dimensions n by m. The bar is made up of n m smaller 1 by 1 squares. Unfortunately, Alice has to share part of chocolate with Bob. At most once, Alice can break the rectangular bar into two small rectangles, either by breaking vertically or else a horizontal cut. She will then give one of the pieces to Bob and keep the other for herself. The two smaller rectangles must have an integer dimension. Note that Alice can also choose not to break the bar and give entirely to Bob. That is also one of the choices. So Bob won't be happy unless he receives at least k of 1 by 1 squares of the chocolate. That's what's the largest number of squares of the chocolate Alice can keep with her while ensuring the Bob is happy with what he receives. So basically, he was like Alice. She was having a rectangular bar of chocolate. She was supposed to make at least like at most of one cut. So with the help of this one cut, we need to figure out whether we are able to somehow able to give the amount of chocolate that Bob is actually required. So once we are able to give, what is the amount of chocolate pieces that is left over with Bob? Sorry, what that is left over with Alice is what we required. So that is what the actual problem statement expects. Let us quickly go with some examples and let us try to analyze how the actual expected output is varying as per the given problem. So let us say these are the given chocolates which initially the Alice is having. So this is a 3 by 4 chocolate. Out of the 3 by 4, the Bob should be getting 2 slices. Basically mean this is a slice, and Bob required 2 pieces. But if I want to give 2 pieces, I need to make only one of the cuts. Either that should be horizontal or else vertical. So if I try to make a cut horizontal in this way, one cut, I'll be getting like 4 pieces which will be given to Bob, and rest over 8 will be left over with Alice. So this is one way of giving to Bob. If I also try to give in this way, so 8 will be moved to Bob and 4 will be left over with Alice. But anyways, it was said that try to give the minimum number of chocolates, which is maximum or else equal to the k value which is required for the bob. So if I try to cut in this way, so 3 pieces will be going to bob, and the leftover 9 will be left over with Alice. So this is one way of partitioning. If I also try to partition over here 6 and 6. So out of all this, which one do you think is the best optimal way of partitioning? The one that is in this particular way. Yes, I can just simply partition over here. As a partition over here, so 3 will be moved to Bob, and the leftover 9 will be left over with Alice. So how many that will be left over with Alice is what we are supposed to print. So for this, output here is going to be 9. So in this particular example, if it is 3 by 4 and at least like 4 pieces should be definitely given to Bob. So in this particular case, if I try to partition in this particular way, so all the 4 pieces will be left over with Bob, and leftover 8 pieces will be left over with Alice. So I can simply say output for this is going to be 8, because if I try to partition in this way, in this vertical way, only 3 pieces will be given, but with the help of 3 pieces Bob will not be happy. So that is also mentioned in the problem. So all the 4 pieces should be given to Bob. We can also give maximum number of pieces greater than 4. That is also fine, but we need to find the minimum of all this. So 8 is going to be answer for this. In this particular example, this is a 6 by 5 chocolate grid. So out of the 6 by 5 chocolate, I need to give 28 slices, 28 small slices to Bob. So if I want to make this, if I somehow make a cut in this particular way, so out of 6 by 5, so 1, 2, 3, 4, 5, 5 will be given, but he need 28. So this is not the right way. So if I try to partition over here 10, this is also not the right way. If I try to partition over here, this is 15, this is also not the right way. So this is going to be 20. 20 is also not the right way. So it was also mentioned that so note, Alice can also choose not to break the bar at all if she wishes to do. Okay, so if she want to do, she thinks not to break the bar itself. So if I can simply give the entire part to Bob, it's going to be 30 pieces. The leftover part with Alice is going to be 0 in this particular case if you go with all horizontal slices. I can also go with verticals, right? Let us also quickly go with verticals. So if I try to partition in this way, so let us say like 6 pieces will be given to Bob, and leftover will be present with Alice itself. Later with 12 is still less than 28. Later 12, it's going to be 18. 18 is still less than 24, still less. And if you go with 30, 30 is little larger, and we can just make a partition over here. This is one of the ways, or this is one of the ways. So these are only 2 ways in which I can just simply give this amount of chocolate to Bob. So I can just simply say the amount of chocolate that is left over with Alice is going to be 0. I guess it is clear in this way. Let us quickly code the exact same concept. What we're trying to do, can I say we're going to start partitioning on the rows alongside on the columns. Yes, initially I can just simply start with one row, and I can start with one row and go all the way from one row to total number of like one column to total number of columns, alongside one row to total number of rows. So I can just simply make a partition in this particular. Yeah, let us quickly code this part. So even for this, I'm going with Java. So if you look at this particular example for this particular code, scanner class, I'm reading with test cases, and for each and every test case, I need to take n, m as well as the k as the input, and I'm just calling this function max chocolate Alice can keep, and whatever the result that I'm getting, I'm going to print this result. Now let us try to implement this function max chocolates Alice can keep, which is having a parameters like n, m as well as k. So initially, can I say what is the total number of chocolate slices that are available? Yes, it's going to be n into m. So when I say in total is going to be n into m, is the total number of slices that is available. Let us look at some examples. Let us say if the value of k, that if it is 0, let us say the minimum number of slices that should be given to Bob is, let us say, 0. If it is 0, do we need to make some operations on this chocolate bar? Obviously no, right? So what is the amount of chocolate that is left over? Total. So can I say if k is equals to 0, can I directly return the total that is left over, which is going to be left over with Alice itself? Yeah. So this is one way. Let us say if the amount of chocolate that Bob is required, if it is larger than the total that is present, if it is larger than the total that is present, now can I just satisfy the Bob? Obviously no. As I am not going to satisfy, is it really required to give some chocolates to him? Obviously no. So I can just simply make one of the condition. If k, if it is greater or equals to total, basically mean total number of slices. If k is greater or equals to total number of slices, I cannot give any of the slices to Bob to satisfy him. I can directly return 0 over here. Okay. If these two are not the possibilities, I'm left over with few of the things. I could go on slicing horizontally and I could go on slicing vertically. Of the all, whatever is left over, I'm going to take the maximum that is left over with Alice. Yeah. So can I just simply go with a for loop? So let us say int I starting with 1, let us say I less than or equals to n. Basically I mean like n number of, I can also go with all n rows to be given for Bob. So for this reason I less than or equals to n I plus plus. So what I'm going to do is let us say if I want to make a partition over here, I just want to calculate the number of chocolates present over here as well as the number of slices that are present in the both the parts. So this is part A and this is part B. So how many chocolates will be present in this part A? 4. And how many chocolates will be present in this part B? It's going to be 8. So what I mean is, if this is the slice which I'm going to make, if I talk about this is the row 1, if I talk about this is the row 1, if this is row 1 times of the number of the elements which are present in this particular column is going to be the number of slices which are going to be given to the Bob if I make a partition in this way. Yes. So what I mean is 1 times of 4 is going to be the number of pieces which are available in part A, and the leftover 2 rows. I can say 3 minus 1, which is 2 rows times of 4 is going to be the number of pieces, number of slices which are available in part B. So over here I'll be getting 4 and over here I'll be getting 3 minus 1, 2 times of 4 is going to be 8. So 4 as well as 8 over here. Even if I try to make a new partition over here, let us say I want to make a new partition over here, if I make a new partition over here, this is going to be row 2. If I talk about row 2, part A goes to be 8 and part B goes to be 4. So 8 parts in the part A and 4 parts in the part B. And if I try to partition in this particular manner, the one that is having maximum should be left over with Alice, because initially when I make a partition over here, this part goes to Alice. Sorry, this part goes to Bob. Yes, this part goes to Bob, and the leftover part should go to Alice. In the same manner, if I try to make a partition over here, if I want to give this entire part, to Bob, and this part should go to Alice. Yes. So if this is the partition, this should go to Alice, and if this is the partition, this should go to Alice. I guess this is clear. If upper is a partition, the lower one goes to Bob. Sorry, if upper is the partition, lower one goes to Alice. If the lower is a partition, upper goes to Alice. Exactly same. Let us make the two parts. Let us say part A is going to be, if you want to make a partition, let us say, can I say I times of number of slices, basically number of columns. N columns are present, E is going to be the number of slices which are present in part A, and let us also calculate part B is going to be, I can also calculate a total minus PA, which is also fine, but I can also do something like N minus I columns will be present, times of M will be the total number of slices which are present in part B. So I got part A, total number of parts in part A, total number of parts in part B. Now I'm going to check if total number of parts. So initially, let me also take one other thing. I also need to return the maximum number of pieces which I can give it for Alice, which I can put it for Alice. Let me take int max slices for Alice to be 0, and let us try to go with this particular thing. If the part A, if it is greater or equals to k, that is what the condition, right? number of chocolates, if it is greater or equals to k, then only I can make a partition and I can give some of them to Bob. If it is greater or equal to k, I can say the amount of chocolate which is left over with Alice is going to be part B, and if that is a maximum, I'm going to include it, or else what is a maximum that I'm going to include. So I'm going to say maximum slices for Alice is going to be math dot max of maximum slices that Alice has, alongside, as I'm going to make the partition for part A for Bob, so part B will go for Alice. I guess this particular thing is clear. In the same manner, if I want to go with if I want to go with giving the part B to Alice, if I want to give part B to Alice, I should firstly ensure the part B is greater or equals to K. If it is greater, the amount of part that is left over for Alice is going to be part A, and I'm going to give part B to Alice. I guess these two things are clear. And this is for all the rows. This is for all the rows. And can I do the same operation for columns as well? And for columns, I'm just simply copying the same code. I starting from 1, I less than m, I plus plus. Let us say part A is going to be I into n, because I'm going to make the partition as the column. The number of slices which are present in the first column is going to be n in this particular way. I into n will be the number of slices in the particular column, and later m minus I times of n will be the leftover part B. If the part A is greater or equals to k, I'm going to say maximum slices of max as well as part B if it is not part A. And out of all, what I need to return? Return maximum slices for Alice. Let us once again look at the entire part. So total is going to be n into m. Maximum slices I just initialize to 0. These are two conditions based on which we are supposed to act, and later the possibilities, I can just go on with rows I starting from 1 to n. I can also go on with columns I starting from 1 to m. So if it is rows, the number of parts which are present in part A is going to be I into m, and n minus I into m for part B, and out of which I'm going to take the maximum if it is greater or equals to k. In the same manner, if I go on with columns, I into n will be the total number of slices which are present, and m minus I is the number of columns which are left over, and for each and every column n slices are available, n m minus I into n. If the part A is greater or equals to k, I'm going to say the max of part B with the max of slices of Alice, and if the other case, maximum slices of part A, and this is going to be the overall. I've also written, I took the output and just trying to print this. Let us try to run this and see if we are getting the exact same output. Yeah, so part A, part B. I need to declare the identifier int. Let us also see if we got something else as errors. Symbol is not found. Fine. Yeah, everything refers to the same. Everything refers to the same. So we got some output. Let us also try to compare with this sample input and output. So we got 9803625. It is exactly same. Let us also try to submit this. Yeah, all the discuss got passed. Yeah, moving on to the next problem, incremental game. Alice and Bob found two piles of stones, one with X stones, another with Y stones. They decided to play a game using these piles. Alice and Bob are always trying to one up each other. Basically, they want to win up each other. So they decided to play under the following rules. The players take turns moving with Alice going first. On Alice's first move, she must choose one of the piles and remove at least one and at most k stones from that pile. She is having a chance of like removing at least one or else at most of k in the first time. Okay. Thereafter, after the first time, each player will choose one of the pile and has to remove strictly more stones from it than the opponent's previous move. Basically, let us say like if Alice has picked like 4 in the first time itself, from the next time Bob should pick 5, which is greater than the previous, which Alice has took, which is going to be 5. More than 5 should be picked. Okay. For instance, if Alice removes 3 stones in the first turn, Bob's next move must remove more than the 3 stones, which is going to be basically starting from 4. Okay. Note that there is no upper bound on the number of stones that can be taken, except for Alice, the first move, which is bounded by k. Okay, in the first time itself, there is an upper bound. Only at max of k can be taken, at least of 1 can be taken, and then after, there is no upper bound for this. Okay, whichever player who is unable to make any move loses the game. If both players optimally aiming to win, who will win? Okay, this is a given problem statement. You're given x, y as well as the value k as the input, and for each and every time you're supposed to say who is the winner of this particular game, either Alice or else Bob. Okay, and if you also look at the constraints, number of test cases are at like 8,000, and x, y, k values are nearly like 20. Seems like a little smaller constraints. Okay, if this is a given example, these are the given output. I guess the problem statement is clear. Let us quickly discuss some inputs from this particular problem statement. Let us say these are the 2 piles which are present with Alice as well as Bob. And it was mentioned in the very beginning, Alice has a chance of picking either 1 or like basically at least 1 at max of k only in the first time. Only in the first time. Okay. And from later on, let us say if Alice has picked like some 4 over here, and from them, Bob should either definitely pick greater than 4. Okay, if Bob picks something which is greater than 4, and Alice should pick something which is greater than which already Bob has picked. So in this particular way, the one who is left over with no coins of picking will loses the game. The opponent wins the particular game. Okay, let us quickly once again look at this particular example. There are 4, 4 and 10. 4, 4 and 10. Basically saying that 4 coins in the first pile, 4 coins in second pile. And out of these, I need to pick like the value of k is also given as 10. If 4, 4 are given, I can directly take like 1, 2, 3, 4. 1, 2, 3, 4. So k value is 10. So Alice wisely plays a game. So what she does is, she directly take all 4 from this. If I take all 4 from this, the leftover part is like 0 on the left and 4 on the right. Okay, 0 on the left and 4 on the right. So what Bob should pick? The value which is greater than 4. Do we have a chance of picking greater than 4? Obviously no. So Bob loses, Alice wins. This is a given game. So as a constraint says like the value of n, m, k, I guess like x, x, y as well as k, right? Yeah, x, y as well as k, y as well as k is less than or equals nearly 20. As it is nearly equals to 20, why can't we simply go with each and every possibility in this particular case? Yes, obviously we can go with each and every possibility, which basically mean if I can simply take one coin, what I mean is I want to take one coin, basically one stone, and give it to Alice, sorry, give it to Bob, and let us make Bob to play now by picking either like greater than one stone from this. Okay, in this particular way. Later, I just want to pick 2 and give it to Bob and see what Bob picks. Based on that, I am going to decide. So out of all this, if something which is actually favoring me, I'm going to choose a particular path. So I am having lot many paths. Out of all the paths, the one that is favoring me, I'm going to choose that particular path. I guess a little bit is clear about this particular thing. So what I'm basically going to do here is I'm going to explore with all the possibilities. Basically, as the constraints are very low, I can just simply go with some kind of backtracking logic, some kind of recursion logic for this. So initially, as it is Ali's turn, she should either pick one, at least one, at max of k. So I can just simply go with one coin and give it to Bob. Either go with 2 coins and give it to Bob, 3 coins and give it to Bob, 4 coins and give it to Bob, and so on. Yes, as we go on in this particular way, when can you say a particular person will loses? When can you say a particular person will loses? Can I say if there is a last picked number of coins, if the leftover coins in either pile A or else the leftover stones in pile A or else pile B, if it is less than or equals to last, can I say the person who started over here, the person who is supposed to pick over here will definitely lose? Yes. So I can just simply consider this as one of the condition, and I can just simply move further by going with my backtracking logic as my base. Okay. Let us quickly go back to this particular thing and let us cool it up. Okay. Uh, if you go with the input, first line of input contain t the number of test cases, letter x, y, k. Okay. Here I'm going with Python to code this up. Let us say for in range of input x, let us say x, y, k equals to map of int comma input dot split. Okay, so over here I'm just defining some function. Let us say some kind of void function. Let us say def winner, which takes the parameters x, y alongside the k. Okay, so internally inside this function, what I'm trying to do is, as I'm not really required with this x, y, and k each and every time, can I go with one other function, nested function? Let us take this function as a boolean function. Let us say this is a can when, basically says, let us take the parameters as like x, y, and last picked. Okay, for better sense, let us take like left x, basically leftover x, left y, basically leftover y, leftover coins in y, leftover coins in x, and what is the last picked? Okay, what is the last picked? Can I say at each and every point of time I'm having a chance like either pick the number of coins which is greater than the last coin, greater than the last picked? Yes. So can I just simply go with for stone in the range, that is not supported, right? Stone in range of, so what is last pick? I need to pick one more than the last pick at least. Yes, one more than the last pick. And what is the maximum that I can pick? Yes, maximum that I can pick is the coins which is left over in X. Let us say if I want to go with X, the maximum which I can pick is going to the leftover which is X. So can I say left X is going to the maximum which I can just simply pick. Okay. As this is inclusive, I can just simply, as this is exclusive, I can just simply go with left X plus 1. Left X plus 1. The stones which I want to pick should be at least one greater than the last picked, and it can be one greater than the last pick to the maximum number of coins which are present in the particular pile. If I want to go with X, the number of coins, the number of stones which are present in this pile is going to be left X. Okay. So if this is a case, the stones which I'm going to pick is going to be last pick plus 1 for the first time, last picked plus 2 for the next time, last pick plus 3 for the next time, as it goes on, leftover X for the last time. Okay, as we go on in this particular way. When can I say I can win? When can I say I can win? I can say this function will actually decide whether a person can win or lose a game with the leftover X pile, leftover X stones in pile X, leftover Y stones in pile Y, with the last big number of coins. Okay, with the help of last big number of coins. So if I want to do this, let us say if I want to win, can I say for the next time if I give last picked as the number of stones, can I say the opponent should definitely lose? Yes. So can I say if not can win? Okay, basically can win, cannot win. Basically if cannot win with how many coins? As I'm trying to pick it from pile X, the number of coins that are left over in pile X is going to be left X minus stone number of coins, left X minus stone number of coins are present in pile A, and how many coins are present in pile B, basically pile Y, it's going to be Y number of coins, basically left Y number of stones which are present in pile Y. Okay, and how many stones do I have picked now? Stone number of, okay, stone. So if opponent cannot win with this particular strategy, can I say I can win? I'm going to return I guess this particular thing is clear. What I mean is, I'm going to start with the last pick plus 1 and I can end at left x plus 1. What I'm saying is, if the left x minus number of stones, if I give this as a possibility alongside the left y as a possibility and say the opponent is playing, if I give this as a possibility, if he is not able to win, can I say I'm going to win? Yes, this is the thing. In the same manner, I'm also having a possibility of picking something from pile y. So can I say for stone in, okay, range of last pick plus 1, left y plus 1, okay, if not, can win of leftover x will be exactly same, leftover y minus stone will be the number of coins and stone are the coins that I have picked. If this is the case, return true. If any of these cases does not satisfy, return false. Okay. And coming to this base condition, when can I say a person loses? When can I say a person loses? Can I say if the leftover x, leftover y, if it is less than or equals to the last picked, if it is less than or equals to last picked, can I say obviously the person who is supposed to play will lose? Yes, if left x, if it is less than or equals to last pick, and I should have the same condition on the pile y as well. If I'm having a possibility of picking some coins from the pile y which is greater than the last pick, I can pick it now. If that is also not the possibility, then I can lose. So if left y, if it is less than or equals to last pick, I can return false. Okay, I can return false. As of now, we are only discussing like who can win. Basically, what is the, like if this is a possibility, if he can win. Okay, so can win which takes leftover x, leftover y, and last picked. If leftover x is less than or equals to last picked, or and leftover y if it is less than or equals to last picked, obviously the one who are supposed to take will lose. I'm going to return false. So let us say for each and every possibility from last picked plus 1 to leftover x, and for each and every possibility from last picked plus 1 to leftover y plus 1, if someone with starting with this does not win, I can just simply say I'm able to win. This is a possibility. In the same manner, not picks left x, left y minus the number of stones, and the stones is the stones which I have picked currently. Okay, return true. So this is all about the thing that we have seen. And later, as it was said, Alice, let us once again go to the problem statement. As it was said, on Alice's first move, she should choose one of the piles and remove at least one and at most k stones from the pile. So that means, can I also take this as a possibility and start from 1, 2, 3, 4 and so on until k? So yes, I can also go with this particular thing. What I mean is, so let us say first picked in the range of 1 comma k plus 1, let us say, like I can pick 1, I can pick 2, I can pick 3 and so on until k. I can also pick k. So for last picked in the range of 1 comma k plus 1, and if I want to pick, let us say if I want to pick it from x, pile x, let us say if I want to pick it from pile x, so can I say the number of the first picked coins should be obviously less than the x value or less than or equal to the x value? Yes. If first picked, if it is less than or equals to the value x, initial value of x, okay, so this is going to be k plus 1. Okay, if first picked, if it is less than or equals to x, and can I say if I'm trying to pick these many number of coins, and if I'm trying to give this as a possibility to my opponent, if the opponent loses, can I say I can win? And obviously this is the first time that Alice is starting. As Alice is starting, if opponent loses, can I say Alice wins? Yes. And if not, can win of, as I want to go with pile x, the number of coins which are present on the pile x are going to be x minus first, let me copy this, x minus first pick, and later the number of coins which are present on pile y is going to be y alongside how many coins which I have picked is going to be first pick. Okay, so if the first picked, if it is less than or equals to x, alongside if the opponent loses, I can say Alice wins. As is a void function, I'm going to directly return string whoever wins. Let us go with the spelling of Alice once. ALICE. Yeah. Let me copy over here. Alice wins. Okay. And it is only the possibility. Can I also go with the pile y? Yes. Yes. Obviously, I can go with the pile y. Let me just copy this. Okay, first picked in the range of 1 comma k plus 1. If the first picked, if it is less than or equals to y, and then we know of x minus, so x should be exactly the same. I am going to go with y minus first picked, and the first picked, if opponent loses, I'm going to say Alice wins. If this is not the case, return Bob wins. Okay, I guess everything is clear. Let us just simply call this function. Yeah, print winner of x, y, and the value k. Let us once again look at this entire logic. I just took a void function winner x, y, k, which takes x, y, k, inside which I'm having a boolean function which actually says if a person can win with the left x, left y, as well as the last big number of coins. Okay, so I know the base condition saying that if the number of leftover coins, if it is less than or equals to last picked, or is the number of leftover coins, and y if it is greater or equals to last picked, if both the conditions satisfy, I cannot have a chance of picking. I can just simply say I am going to lose this. So I'm going to return false. If this is not the case, I'm having a possibility of picking either last pick plus one number of coins till starting from here till leftover x plus 1. In the same manner, last pick plus one number of coins till leftover y plus one number of coins. If the opponent loses with this given number of coins, I'm going to return true. If this is not the possibility, finally I'm going to return false. And as the first chance of picking is starting from 1 to k plus 1, basically 1 to k number of stones. So if Alice picks first pick number of coins, and if it is less than or equals to x, I can just go with x minus first pick, y number of coins, and first pick. And if this is a possibility that opponent loses, I'm going to say Alice wins. If this is a possibility that opponent loses, I'm going to once again say Alice wins, as Alice starts it first. Okay, and later return Bob. Let us quickly run this and see if you're getting exactly same as expected. For first picked in the range of invalid syntax. So yeah, anyways, the will not be present, right? First picked in range of. We got like Alice, Bob, and Alice. Let us try to compare with the sample input and output. Yeah, Alice, Bob, and Alice. Let us try to submit this as well. Yeah, all the test case got passed. Fine. So as the constraints are little lower, as the constraints, the value of x, y, k are little lower, we went with this kind of backtracking logic, which actually worked fine over here. Yeah, going with the next problem, or what? You're given two positive integers n and x. Find any permutation p of integers 1 to n such that the number of indices I is in the range of 1 to n, satisfying pi bitwise or with I is equals to x. Is as large as possible, which basically says the number of indices which satisfy should be as large as possible. Yeah, here this basically, yeah, bitwise or a permutation of integers 1 to n is an array of length n which contains every integer in the range of 1 to n exactly once with different arrangements, which basically says permutation. If there are multiple permutations that maximize the required count of indices, you may find any of them is going to be output for this. So finally, you're supposed to print a permutation with this given length n. So if it is 5, this is a permutation with length 5, permutation with length 5, and you're also given this value 1, as it says x is the value 1, and over here as the value of x is equals to 1, I need to somehow manage such that I'll be getting pi or with I is equals to x should be as maximum number of indices as possible. I guess the problem statement is clear. Let us quickly go with some kind of math in this, and let us make it clear for solving this particular problem. If we look at the constraints, t less than or equals to 10 power 5, n less than or equals to 2 into 10 power 5, x is less than or equals to 2 into n. Fine. Okay, moving on to this. As it says, always pi or with I should be equals to x. Pi, which basically, let us say a permutation is present. Pi basically indicates a value at ith index, and the indices are starting from 1 over here. This is first index, second index, third index, fourth index, and fifth, and so on. Pi is a value present at the second ith index. Let us say if this is I, pi is the value that is present at ith index. Okay, what he says is pi or with I should be equals to the value x. You're given n, you're given x, you're supposed to find the maximum count of such values pi or with I should be equals to x. If there are maximum, like if there are two or three such permutations which has the maximum number of possibilities of which satisfies this particular condition, and to print that particular permutation. That is what the given problem statement. I guess the problem statement is clear. So moving on to this, understanding about some math in this. Pi or with I equals to x basically says P of I or with I should be equals to x. P of I or with I should be equals to x. So when this could be a possibility? Can I say if pi or with I, if it should be equals to x, can I for sure say P of I should be definitely less than or equals to x? Alongside, can I for sure say I should be less than or equals to x? Yes, at any possibility, if it is greater, if this is greater, or else if this is greater, can we get a value which is equal to x? Obviously no, right? Obviously no. So obviously P of I should be less than or equals to x, and alongside I should be less than x. These two things. Moving ahead, let us take some example and let us see how we are actually getting this. So if you look at this third example, 4, 6, we got 3, 4, 1, 2 as output. 4, 6, 3, 4, 1, 2. So if you take about this 4, 6, 4, permutations of 4 are going to be 1, 2, 3, 4. I can go with 2, 1, 3, 4. I can go with 2, 3, 1, 4. I can go with 2, 3, 4, 1, and so on. A lot many permutations will be there. I guess a lot many permutations in this particular way will be there. If I want to go with the brute force, I can generate all the permutations, and out of all the permutations, I can just simply perform this operation pi. This is the pi or with I, the index which is present. This is first index. Let us say the indices. This is first index, second index, third index, and fourth index. When I try to perform the bitwise or with this particular index alongside the pi, if I get the maximum number of values which satisfy the value x, I can include this as a permutation as my answer. And over here we get the answer is something like 3, 4, 1, 2. 3, 4, 1, 2, which basically says the value of x is equals to 6, the value of n is basically 4, and which is a permutation which we got, which is having maximum number of. Let us see how we got the maximum. Yes, so 3 is represented first index, 4 is presented second, third, and fourth. So if I try to perform 3 or with 1, the the binary value of 3 is going to be 0, 1, 1, and if I try to perform OR with 1, it's going to be 0, 0, 1. So if I try to perform OR with this, are we able to get 6 over here? Obviously no. And if you go with 4, let us say, the binary value of 4 is going to be 1 0 0, and the value index over there is going to be 2, and it's going to be 0 1 0. And if I try to perform OR over here, if I try to perform bitwise OR over here, it's going to be 0, it's going to be 1, and it's going to be 1, which basically says 4 plus 2, which is going to be 6. Yes, it satisfies. Basically this satisfies. And alongside, if I also go with even more, if it is 1, the binary value of 1 is going to be 0 0 1. The binary value of 3 is going to be 0 1 1, and this is once again not as expected, which is not equals to 4. And if I take about 2, the binary value of 2 is going to be 0 1 0, and for 4 it's going to be 1 0 0. And if I try to perform bitwise OR, we'll be getting 0 1 1, which is equals to 6 once again, which once again satisfies. Maybe none of the subsets which actually gives us the maximum, which is equals to 2. Maybe few of them might be giving us 2, so I can say this is one of the permutation. And if I also want, I can also write something like if I also want to write, I can write something like 1 4 3 2. So 1 4 3 2 also is going to be output for this particular example. 1432 also is going to be output for this particular example, because this is at index 1 2 3 4. And when I try to perform this bitwise or with this value alongside with this particular index, so 1 or with 1 is going to be 1, it is not equals to, it is not equals to 6, so it is not satisfies. 4 or with 2 is going to be 6, 3 or with 3 is going to be once again 3, 2 or with 4 is going to be 6. These two satisfies. So this is also another permutation which I can return. Maybe the given code will actually also accept. This is also a possible answer for this given particular problem. I guess the problem statement as alongside a bit logic of how we are getting this particular example, particular permutation is an answer is clear for everyone. So moving ahead, can I do something like this? Based on our observations, as of now, we got something like the value pi should be always less than or equals to x. Alongside, we also find something like I should be less than or equals to x. Pi should be less than or equals to x. Alongside, I should also be less than or equals to x. Yeah. So let us say something like this. We got 4 or with 2 is equals to 6, and we are having this x with us, we're having this as the index I, and we're supposed to find this value. Basically, we're supposed to find this value. Can we somehow get this value with the help of this I as well as x? If we can somehow know a value I as well as x, yes, let us try it. Let us say I just want to perform 6 XOR with 2. 6 XOR with 2. The binary value of 6 is going to be 1 1 0. The binary value of 2 is going to be 0 1 0. And if I try to perform XOR over here, I'll be getting 0 over here, 0 over here, and 1 over here. And what is this value? Can I say this value is going to be the value 4, which I am required as the value which I am expecting? Yes. If I also go with something else like 4 with 2 or else 2 with 4, everything is going to be exactly same, right? Yeah. So this associative property actually satisfies in bitwise operators. So I can just simply go with 4 XOR with 2 or else 2 XOR with 4, which actually satisfies. Like 6 XOR with 2 is going to be 4, or else 2 XOR with 6 is once again going to be 4. Or else if I try to perform like 6 XOR with 4, I'm going to get 2. Yeah, so I'll be getting 2. So as I'm getting this 2, as it is a permutation, can I also validate whether this value 4 is already taken or not? If it is taken, I'm not supposed to take this, right? Yes. If it is not taken, then I'm having a chance of taking this 4 to my output at that particular index I. I guess this particular concept is clear for everyone. Let us now try to make some code for this with this given particular logic. Yeah, let us first go with the input first. The first line will contain a single integer t, later nx. Okay, n as well as x. Okay. prime range of n of input n comma x equals to list of map of input dot let. I took n as well as x. Let us first go with some function def. A good name for this is or what or what or what, which takes n as well as x as the parameters. As we all know, we need to somehow figure out, or else we need to somehow frame a permutation. Yes. So for this permutation, let us say a permutation p is of size n plus 1 with all zeros. Let us say it is a permutation starting from first index. Let us go with first index. Let us eliminate the 0th index value later on. Okay, let us say there is a permutation p with all zeros of size n plus 1. Along with this, as I said, value which we have already taken should not be included in the permutation, right? So for this reason, can I say we also require something called visited array. Visited is going to be of false of size once again n plus 1. Okay, with the help of it, I'm going to figure out whether it is already taken into my permutation or not. Yeah, let us first simply iterate for I in range of 1 to n plus 1, n plus 1. So basically, I need to start iterating from first index to nth index, and to place some value in the permutation array which I have already declared. So initialize. So I'm going to iterate from 1 to n plus 1. As we are able to figure out, as we already figured out, if I'm already having this value I, if I'm already having this x, if I'm already having this value I along with this value x, I will be able to figure out this value with the help of this particular XOR logic, x XOR with I. Yes, x XOR with I. Let us go with the same. So let us say value equals to x is already present, XOR with I, x XOR with I. Okay, and whatever the value which we got, and it should be, as the problem states, the value whatever we got, which we are supposed to place it in the permutation, it should be in the range of only from 1 to n. Yes, as it should be only in the range of 1 to n, can I also validate if value or else 1 is less than or equals to value is less than or equals to the value n plus 1 or else n. Yeah, if value is in the range of 1 to n, that means maybe this is a possibility. Yes, if this is a possibility, firstly I need to ensure if it is already taken or not. Yes, if visited of value, if it is false, can I say I can take this? As I can take this, I can say p of I at this particular index, I want to place this value. P of I is going to be value, and as I have already taken, can I also mark this visited of value to true as I have done taking this? Yes. So what I'm trying to do is I'm going to iterate from 1 to n plus 1. I'm going to get the value as value is going to be x XOR with I, and whatever the value that we get, I'm going to check if it is in the range of 1 to n. If it is in the range of 1 to n, I'm going to check whether it is already taken or not. If it is not taken, I'm going to say p of I is going to be value. P of I is going to be the value, and I'm going to say visited of value is going to be true. Yes, done with this. So once I'm done with this entire iterations, let us see what we will be getting to the output. Let us try to print this visited. First, let us try to print this visited. Let me call this function or what, which takes the parameters n alongside x. Right? Yeah. Let us try to run this and see what we're actually getting. Uh, we are getting actually a small input issue, I guess. Nx equals list of map of int comma input dot split. What it says, built-in function or method has no attribute split. Okay. N comma x is going to be list of map of int comma input dot split. Yeah, so we're getting a boolean. So instead of printing visitor, let us print the value. Let us print the permutation which we are trying to frame it. Okay. So we got the permutation as let us go deal with this third example, 4 and 6. For 4 and 6, at second index as well as the fourth index, we got 4 as well as 2. At fourth index as well as second index, we got 4 as well as 2. That means we are able to somehow frame this permutation at this particular indices. And for the leftover zeros, can we place the leftover values which are not being taken in this particular permutation? Yes. And for this, can I write one more piece of code? Okay. For let us say I in range of 1 comma n plus 1. Let me go with the next value which I want to take place. Okay. Next value is going to be 1. Let us say the next value which I want to place is 1, and let us assume like it is 1. So I'm going to see if something is already placed at the particular index or not. Yes, if p of I, if it is still 0, basically it says nothing is already placed, as nothing is placed, something I need to place over there, right? So what I need to place, I can place 1, I can place 2, I can place 3 if these values are not taken. So for this reason, I'm already having like next value. I'm going to check if visited of next, it is not given, nxt, visited of next value, if it is equals to false, basically it says this is not taken. As this is not taken, I can place it over there. Or in other terms, can I go with a while loop saying that if visited of next value, if it is true, can I increment the visited? Can I increment the next value? Next value plus equals to 1. Okay. If instead of next value, if it is true, I'm going to say next value plus equals to 1. So once I got the next value, can I say P of I is going to be next next value, and can I say visited of next value to be true? So saying that next time I'm not supposed to use this next value which is already taken into my population. So initially I took the next value as 1, and I'm going to iterate I starting from 1 to n plus 1. If p of I, if it is still 0, which basically says I'm not done taking any value, I haven't placed any value at that particular index in the permutation, I'm going to check if something is not taken. Next value, if next value is not taken, I'm going to say I need to place this. If it is already taken, I'm going to go for the next value, which is next value plus 1, next value plus 1. Later, p of I, as it is not taken, p of I is going to the next value, and visitor of next value is going to be true. And later, let us now print the permutation, and let us see what we're actually getting to the output. So we got a permutation like 13254. Let us also try verifying with this input. So 13254, yes, 13254. Just try to consider from first index. Okay. For the next one, 312, if you go with the second example, no matter what permutation is taken, there will be no index satisfying pi or with I is equals to 4. So any permutation of 1 to 3 is a valid. So I can say 312 is a permutation which is valid. I can also say 132 or else 123 is also a permutation which is valid. Moving to the next one, 3412. As discussed previously, 1432 is also valid permutation. 3412 is also valid permutation. See, if you look at this, 3412 is also valid permutation. 1432 is also a valid permutation. We got one of these. In the same manner, if you also look at this, we got some other permutation which is also valid in this particular way. So before moving to the final one, we need to print without an array. So what I'm going to do is, let us say print p else for I in range of 1 to n 1 to n plus 1, print p of I comma end with some space over there. And once this is done, go for a print statement. Let us try to run this. So we got some output. So 1 3 2 5 4 3 1 2. Yeah. So even if I try to submit this, as I'm printing in multiple print statements, there could be a possibility of time wait. But anyhow, as we optimized it a large, because this is a big O of n complexity, even we are trying to go with a lot many print statements, it is working perfectly fine. All the test cases were passed.
I guess all the problems that we discussed in this particular video are clear for everyone. For more content like this, please like, share and subscribe to our YouTube channel. Stay tuned for the next video. Until then, code evolve.